Hi, I'm Juyong Ryu, and I will give a final report on the review of the paper Fairness for Image Generation with Uncertain Sensitive Attributes. And to give a short introduction, consider a generative procedure where we have a user X star in a protected group Ci, and Ci can be race, gender, and so on and so forth. After some lossy observation, we get an image Y. Then a reconstruction creates X hat. In this diagram, let's say Ci is African Americans. Then the top X hat is in Ci, while the bottom X hat isn't in Ci. This paper aims to keep fairness in terms of representation, even if C is unknown. So now that we know the problem setting, we have two questions to answer. The first is, what is a good definition of fairness? And the second is, how do we satisfy such definition? The first definition of fairness to consider is representation demographic parity, or RDP. RDP says that the probability of X hat being in Ci given X star is in Ci is the same for any group. Let's also define another term obliviously. An algorithm satisfies a fairness definition obliviously when it is fair for any choice of C and doesn't require C for reconstruction. And in fact, an algorithm that satisfies RDP obliviously only if it achieves perfect reconstruction. However, since perfect reconstruction is impractical, RDP can't be satisfied obliviously. This poses some moral challenges, since this means someone needs to choose C, which introduces personal bias. And defining minority or races is a different task, since minorities are ill-defined and races are multidimensional. So the act of choosing C itself only reifies the status quo while smoothing over some historical and social context. So this means that we need to consider other fairness definitions. The first is proportional representation, where the output demographics match the input demographics. There could be a harsher definition called conditional proportional representation, where the demographics match even when conditioned on the image. An interesting theoretical result from the paper says that if there is a majority group in C, and the measurements can cause confusion between the protected groups, then RDP and PR can't be satisfied at the same time. Therefore, we can see that RDP and PR are incompatible definitions. Okay, but the most important question is, can CPR be satisfied obliviously? The answer is yes. So the reason is we have an example of an algorithm that will satisfy CPR obliviously. This is posterior sampling. Basically, we sample X hat from the distribution of users conditioned on the image. Interestingly, posterior sampling is the only algorithm that obliviously achieves CPR. And since this is probably the most important theoretical result, I would like to briefly outline the proof. So let's say that we are given a measurement, measurable set, an algorithm that satisfies CPR. Then the probability that AY is in U given Y, or QU given Y, is the same as probability of U given Y. If we look at the total variation distance between the two distributions, then the difference is always 0 for any choice of U. So therefore, the distance should be 0. Thus, QU given Y is PU given Y. Another useful condition that we want is symmetric pairwise error, or SPE. And this means that the confusion matrix is symmetrical. Theoretical results in the paper say that CPR implies SPE and SPE implies PR. Also, reweighting of the input distribution and posterior sampling from this distribution can be used to satisfy RDP. Another interesting characteristic of CPR is that representation cross-entropy is minimized when an algorithm satisfies CPR. Therefore, we can see that posterior sampling is the only algorithm that minimizes RCE obliviously to the partition. Now, to summarize, we wanted to look at fairness in representation, and because of various moral issues, we want a definition of fairness that can be met obliviously. This answers the first question. Now, we want to know what algorithm to use to satisfy it. This is posterior sampling. So next, I would like to go over the experiments done in the paper and their results. How does the paper go about doing their experiments? For implementation of posterior sampling, Langevin dynamics is used. This does noisy gradient ascent on the log of probability distribution to get an approximate to the actual posterior distribution. A generative procedure or measurement is needed to define the probability distribution x given y. A classifier is often needed to identify the groups that the input and output belong to, and we use these in conjunction to see whether or not the various definitions of fairness are kept. The first experiment done was with the MNIST dataset. These are handwritten digits, and the variational autoencoder was used. The protected groups were digits 0, 1, 2, 3, 4, and those greater than 5. The posterior sampling results show that the confusion matrix is nearly symmetric, and therefore SPE is satisfied. This means that PR is also satisfied. The second experiment uses flicker faces dataset, which are images of human faces. These images were 32 times downsampled, and this downsampling was the measurement part. The examples are shown on the right-hand side. For reconstruction, posterior sampling using NCSN version 2 and pulse using StyleGAN2 were compared. The high-resolution images were classified using CLIP, and these 4 classes were used. The confusion matrix shows that posterior sampling satisfies SPE and PR since it is symmetric. Also, some example results are shown on the right, and we can see that posterior sampling seems to represent the user better than pulse. Now, the last set of experiments used AFHQ cats and dogs, and various training and test sets were used, with the ratio between the cats and the dogs being changed. The ratio was the same for the test and training sets. The measurement was downscaling to different resolutions, from 1:1 to 8:8. For posterior sampling, the prior of latent variables and generator network was used along with the Langevin dynamic. Pulse using StyleGAN2 was used for comparison, and for the classifier, ResNet 108 was used. The number of errors and the error ratio is shown for the 20% and 80% cat cases. For posterior sampling, the error numbers are same for each class, so SPE and PR is satisfied. However, we can see that the pulse has a higher error ratio for the minority class. The same tendencies are shown in the 80% case. Therefore, we can conclude that posterior sampling satisfies SPE and PR on unbalanced dataset. The results for the balanced dataset is shown as follows. The number of errors seems to be quite balanced for both pulse and posterior sampling. Thus, they both satisfy SPE, PR, and RDP. The 1:1 case is a slight exception for pulse. Lastly, the resolution was fixed as 4:4 and the bias was changed. This showed the error ratio to be nearly 0.5 for almost all cases when doing posterior sampling. Therefore, SPE is satisfied. Now, to move on to the results reproduction, I wasn't able to finish the reproduction. My plan was, given measurement and training set and a user, I would create a type of conditional training set where the measurement outcome is similar to the user's measurement. Then I would use this to train a score network that would approximate the gradient of the posterior distribution. Then I would do Langevin dynamics to get x hat. And this would be basically the protocol when we don't know the prior distribution. Lastly, I would like to move on to some discussion and the conclusion. There are some limitations to CPR. First, obliviousness causes symmetry in the number of errors, so minority groups will have higher error rates. Also, CPR treats members of all groups equally, and there is also another moral debate we could have on whether or not minorities should get particular attention. Also, CPR only focuses on representation, not quality of construction. Therefore, this is only a piece of a large puzzle that is fairness. So in conclusion, this paper gave multiple fairness definitions and argued that obliviousness is important. They gave CPR and posterior sampling as a good definition and algorithm to keep fairness. Experiments showed that posterior sampling could be implemented using long-driven dynamics, and the posterior sampling satisfies SPE, PR for unbalanced datasets, and also RDP for balanced datasets. And with that, I would like to conclude my part of the final video. Thank you.
Hi, I'm Sean Park, and I will present a review on MCMC variation inference via uncorrected Hamiltonian annealing. Here are some backgrounds. Variational inference is the method to do approximate inference on the target distribution P where normalization constant Z is known. The general method is to utilize this equation. Here, elbow, evidence lower bound, is lower bound of Z since scalar divergence is always non-negative. Since maximizing elbow is equivalent to minimizing scalar divergence from Q to P, we tune parameters of Q to maximize elbow. Recent work have shown that we can get tighter bound and therefore better approximation with augmentation technique. Let P from Z1 to Zm is augmented density of original distribution with the same normalization constant. Still, augmented elbow is lower bound of log Z. Also, augmented scalar divergence is upper bound of original scalar divergence due to chain law. Therefore, marginal Q over Zm approximates target distribution. A successful approach for creating augmented distribution is AIS, another important sampling. It creates an augmented proposal and target distribution by applying a sequence of transient densities. The ratio needed for elbow is given like this. To define the transition Tm and Um, AIS creates a sequence of unnormalized bridge densities pi m. Here, pi 1 is close to Q and pi m is close to P. We can now choose Tm to be Markov kernel that holds bridging density invariant and Um to be reversal of Tm with respect to pi m. This means that they are having this kind of relationship. Then the ratio becomes very simple as shown here. This can be evaluated without evaluating the transition densities and can be used to get an expression for low bound elbow. It has been shown that the AIS augmentation may lead to extremely tighter low bounds. Many MCMC methods used to sample from P are based on Hamiltonian dynamics. Here, we create augmented distribution P over Z and rho like this. Here, S is distribution over momentum variable rho. For example, S can be multivariate Gaussian. The separation is direct result of Hamiltonian dynamics and Boltzmann distribution. We can utilize various numerical integration schemes like leapfrog method to evolve system. Hamiltonian equation essentially states that gradient of kinetic energy drives change of position and gradient of potential energy drives change of momentum. In fact, P over Z and rho is exactly invariant if you apply MH step. This alternates with scheme that resamples the momentum rho while holding S over rho invariant. Details are more clear in next slide. It is straightforward to apply Hamiltonian dynamics to AIS. Given that simulation quality M is inverse surface of and has unit Jacobian, corrected Tm leaves bridge densities invariant. Defining Um as the reversal of Tm with respect to pi m, we get this ratio for elbow. Although this method is a strong lower bound, it depends on many parameters. We would like to tune these parameters by maximizing the elbow using reparameterization-based estimators. However, due to MH step, the resulting bound is not differentiable, and thus reparameterization gradients are not possible. The paper proposed UHA to avoid this kind of non-differentiable bound problem. For any transitions Um and Tm, we can define the ratio as this equation. Hamiltonian AIS defines Tm as the Hamiltonian MCMC kernel and Um as the reversal. Although this results in a nice simplification, it is not necessary. Then, why not define Tm and Um without MH step? So the paper proposed to use uncorrected version of transition Tm and Um. They are just that of Hamiltonian AIS without Metropolis Hastings acceptance step. The intuition behind is that transition state is usually accepted with very high probability for Hamiltonian MCMC. This is due to the Boltzmann distribution and energy conservation property of Hamiltonian. This slide shows uncorrected Tm. This slide shows uncorrected Um. Note that corrected Um is reversal of Tm with respect to pi m. Surprisingly, it has been proven by authors that ratio between uncorrected Um and Tm has simple form. Thus, we can express ratio between target and proposed density like this. Algorithm 5 shows how to generate unbiased estimation of elbow. If reparameterization trick is applied, then gradient backpropagation is used together with stochastic optimization algorithm to maximize elbow. The authors used the leapfrog operator with step size epsilon so that simulation is inverse surface of and has unit Jacobian. They set the momentum distribution and resampling distribution as Gaussian. Here, eta is damping coefficient. If eta is 0, momentum is completely resampled. However, for large eta, resampled momentums becomes correlated, which help suppressing random walk behavior. Bridging densities are in this form, so that Q is close to pi 1 and P is close to pi m. With parameterization trick, the paper focuses on tuning initial distribution Q over Z1, sigma, epsilon, eta, and parameters of bridging densities such as beta. Here are some experimental results. We compare UHA with previously studied works. One is Hamiltonian VI. It is like UHA, but there are no bridging densities. And UM is set to learnable parameterized conditional Gaussian. Typically, single transition is used and parameters are learned by maximizing elbow. The second method is Hamiltonian VAE. It is based on Hamiltonian importance sampling. The third method is importance weighting. Using this property, it optimizes right-hand side rather than elbow itself because it is easier. Of course, UHA is also compared with Hamiltonian AIS. UHA is compared with other methods for different values of K. K is the number of likelihood evaluation required to build a lower bound. For example, K is number of samples used for importance weighting and number of bridge densities plus 1 for UHA. Note that for fixed K, all methods have the same complexity. For K equals 1, all methods reduces to plain BI. Here, the target distribution is factorized student T distribution, whose mean is 0, scale is 1, and degree of freedom is 3. Since log Z is 0, it is easy to analyze the tightness of elbow. For UHA, integrated step size epsilon and damping coefficient eta is tuned. This figure shows experiment result. Although UHA performs similarly with importance weighting for low-dimensional target, it performs significantly better when target dimension is high. Therefore, UHA performs better than importance weighting in general. For inference task, 4 models were chosen. Damping coefficient is tuned with Adam optimizer, and integrator step size epsilon is tuned via grid search. For the case of HAIS, both parameters are tuned via grid search since gradient doesn't flow. The experiment results showed that for all values of K and for all 4 models, UHA performs best in terms of maximizing elbow, followed by HAIS. Also, it is clear that UHA, HAIS, and importance weighting performs better for higher K, while HVI and HVAE does not. This agrees with previous research. Due to GPU problem, I was only able to reproduce experimental result in time for a small dimensional dataset, which is Brownian motion. I extended the range of K to 512, which has not been tested in the paper. We can see that UHA still performs better than others. UHA can be tuned with more parameters. For example, sigma can be parameterized diagonal matrix. Beta can be any function satisfying this condition instead of linear. Initial QZ can be learnable, and epsilon can be function on beta, typically affine. Finally, bridge density pi m can be in this form, where Q psi is mean field Gaussian. The experiment on 4 inference model shows that tuning more parameters for UHA leads to significantly better elbow. Also, the result shows that tuning the bridge parameters beta and initial approximate Q over Z leads to a largest gain in performance. Also, tuning larger subset of parameters always outperforms smaller subset. UHA can be used to train VAE. The initial approximation Q and model P are parameterized by 2 neural networks, encoder and decoder. These parameters are trained by maximizing elbow. In the experiment, MNIST, EMNIST, and KMNIST dataset were used. UHA is compared with importance-weighted autoencoders. There are 2 types of encoder and decoder architecture. The first one has only one hidden layer, and second type has 2 hidden layers. It turns out that the architecture of 1 hidden layer performs better than 2 layers, so we only consider type 1 architecture. Figures in the first law shows the achieved elbow, and second law shows the achieved log likelihood. It is clear that UHA leads to higher elbow and log likelihoods than importance weighting for all datasets. The difference of performance between UHA and importance weighting increases as K increases. Moreover, the difference between elbow and log likelihood, which is variational gap, is smaller for UHA than importance weighting. The gap between UHA and the importance weighting also increases as K increases. Therefore, UHA outperforms importance weighting in VA training in general. In conclusion, UHA performs better than other models since UHA yields a differentiable lower bound, which can be optimized via a family of stochastic gradient assets such as Adam. This is possible because there are no image acceptance steps which blocks gradient backpropagation. However, this might sometimes lead to instability during optimization if the step size epsilon becomes large. These effects can be mitigated by restricting epsilon to be small. I'd like to finish my presentation with sincere gratitude for original authors who provided private source code and helped me via email. Thank you.